Record. All right. So today we're going to start chapter 6. Chapter 6, which is probably called something like inference for categorical data. Can't remember exactly, but probably something like that. Okay. Now, for each of these sections, we're going to introduce a new type of question. Luckily, here in 6.1, we've already done 6.1 essentially. The type of question is going to be, the 6.1 type of question is one sample proportion. That's the same as all of chapter 5. We introduce these concepts, confidence intervals, and the hypothesis test. We introduce these with a one sample proportion type of question. Now, we're still going to be in this type of question for today. And then on Tuesday, we're going to start our next type of question in 6.2, which is two sample proportions. That's the first time that we're going to introduce kind of a new type of question. We're still going to build confidence intervals and we're still going to do hypothesis testing. All the rules still apply, all the same rules apply. And so that's nice now that we've kind of sort of learned some rules of the road. Let me just mute everyone because there's a lot of... I tried to change the setting, the default setting, but I couldn't do it on the desktop, but I don't know. That doesn't mean it's not possible, it just means I couldn't do it. 6.3, the 6.3 type is going to be called a chi-squared goodness of fit test. Obviously, we'll deal with that when we get to it. But chi is a Greek letter chi, but it's spelled chi, but don't say chi because then you're found out immediately. So it's chi, chi-squared goodness of fit test. Oh. This is for, so here, today we're still going to talk about one sample proportion. How does it compare to some number, some hypothesized number usually? Then we move into two sample proportions. All of a sudden I have two things that I can compare to each other. That's nice. And then when I move into the chi-squared goodness of fit test, then I have 3+ proportions that I want to compare. What's nice is it is different because all of a sudden we're not using Z anymore, we're using chi, but we only do hypothesis testing, so no confidence intervals anymore. And then the type that we'll see in 6.4 is going to be a chi-squared test of independence. That doesn't mean anything to us right now, but chi-squared test of independence. Then we have two categorical variables with 2+ categories each, which is a contingency table, which we've seen before. Only reason I outline what to expect in all of the chapter is so that it's not, so jarring when every day we change to a new type of question. Okay, because that's what we're going to be doing. So today we're going to do 6.1. Tuesday we're going to do 6.2. Thursday 6.3. And then next Tuesday we do 6.4. I've blocked off for our test. Might be nice to talk about here. Test 2, I've got it on November 19th, which is when? Is that a Tuesday or a Thursday? Tuesday. So test number 2 is on Tuesday, November 19th. Okay. And it's going to be on chapters 6 and 7. Uh-oh, my screen just did something weird. Let me just go check my Zoom room. I'm obsessed. Looks good. I did have reports that the Zoom was a little bit laggy this morning, but hopefully it'll be fine. And we talked about the final exam. Last day, the final exam is on the 18th. Very late, from 9 to 12. So that's nice. It's not an evening exam at least, but late in the schedule. Okay, so a little reminder from the formula sheet before we do. Uh-oh, it's loading. Come on. Unable to open note. Yep, I know. I really want it though. Does that change anything? No. Why is it loading? All right. On our formula sheet, let me see what the order is. I was just going to copy it. We know that the confidence interval for P is P hat plus minus Z star times the square root of P hat Q hat over N. This is a star, that's not very nice. There. So we've already seen that. And we've worked with the confidence interval, although it's been a while, right? So we've got an example of that today. But then we also have the hypothesis test for P. And we outlined all the steps very thoroughly last day. And so we'll do an example today where we go through all the steps again. But what's really nice is even though they are very confusing as we start, right, we're going to use these same steps and the same procedures for all the different types of questions. And so they're worth kind of getting to know and getting comfortable with. We're told that the null hypothesis for a one sample proportion type of question should look like P equals P naught. Now it's up to us to know that P naught is replaced by some number, the number or the proportion you want to compare your sample proportion to. And then to articulate how far your sample proportion is from your hypothesized proportion, we can calculate a z, p hat minus p naught divided by the standard error, which now that I have a hypothesized proportion, I can use that in my standard error over n, p naught, q naught over n. Over here on the side, the conditions, I wasn't really planning for it, but the conditions for a confidence interval, let's see here. I want to highlight that they have the same conditions for the first part. Oops. First part of what, Emily? Whoa, nope, there. Too far. Let's see here, undo, there. Bump them down a little bit. So the independence conditions, the first thing is, do you have a random sample? Right, if you have a random sample, then you can assume that these things are independent of each other. And so that's a good start. And we also have the n less than 10% condition where, okay, if as long as my sample size isn't taking too much of the population, so less than 10% of the population, then I can still assume independence. For the normality condition, it depends on if you have a confidence interval or if you have a hypothesis test, which means that on a test, you would have to read ahead and figure out what it is you're going to do, right, in order to check the correct conditions. For the confidence interval, we need to check that we have at least 10 observed successes and failures. So at least 10 observed successes and at least 10 observed failures. Mathematically, let me give myself just one more, bump it down a little bit. Mathematically, this looks like n times p hat has to be greater than or equal to 10. And this looks like n times q hat has to be greater than or equal to 10. I link these to what I use in my standard error if I need kind of a reminder of what it is, if it's the observed successes and failures, or later for the hypothesis test, we need at least 10 expected successes and failures. So versus for a hypothesis test, we need at least 10 expected successes, which means that n times p naught has to be greater than or equal to 10. But notice that that's the p naught that I use in my standard error for the confidence interval. So these standard errors are on your formula sheet, right? So you can kind of let those be your guide for the conditions as well. Make it slightly less confusing. At least 10 expected failures, which is n times, oops, q naught has to be greater than or equal to 10. So you can use your formula sheet to kind of guide you there through the conditions. if you know your formula sheet well enough, which I would suggest. Okay, nice. The last thing on your formula sheet, kind of new today, is this fun thing that we can do is, given some confidence level and some margin of error, some desired margin of error, we can find the sample size that we would need. So given a desired margin of error and confidence level, we can calculate the sample size needed. In most of our scenarios, we've already collected the sample, or at least that's what we're pretending. But a lot of the time we need to first collect the data, right? If we're going start to finish, we would have to collect the data, and then we can analyze it. And so it's pretty common that you need to figure out what sample size you would need in order to achieve some desired margin of error and some confidence level. So if we take it back, and the margin of error is from your confidence interval, right? P hat Z star times P hat Q hat over N. This is your margin of error, right? This plus minus chunk. We'll do it together, right? But if I have some desired margin of error that I can call M, right, then I might have M is equal to Z star times the square root of P hat Q hat over N. If I am told, okay, I want to be able to report my findings with a 95% confidence interval, then that tells me what Z star should be. And I want to have a margin of error of, let's say, 0.03, right? P hat is a proportion, so it's between 0 and 1. So we can translate them to percentages if you want, right? And then your plus minus your margin of error would be 3% in that case, right? And so usually before you go and publish a paper, you have some idea of what kind of good results would look like. And so what you can do is you can work backwards and figure out, okay, what sample size do I need in order to make that happen? So we can solve for N. Solve for N by first dividing M by Z star. So M divided by Z star. And I am going a little bit quick because it's on your formula sheet. Is the square root of P hat Q hat over N. Gotta add a page here. I can get to the N by squaring both sides. M divided by Z star squared is P hat Q hat over N. Gonna do a little maneuver here. I'm gonna multiply by N, but then I'm also going to divide both sides by M over Z star squared. And so then I get N is P hat Q hat divided by M divided by Z star squared. It's technically a fraction over a fraction. So I get Z star over M squared times p hat q hat, which almost matches what's on your formula sheet, except remember the problem is I haven't collected any data yet. So I don't have a sample proportion because I need to have a sample in order to have a sample proportion, right? And so there's going to be two different options for p hat. Since we have not collected a sample yet, we do not have a p hat, which also means therefore no q hat either. They go hand in hand, right? 1 minus p hat is q hat. Therefore, no q hat, which is 1 minus p hat either. So what we have is, that's okay. On your formula sheet, so instead, we write p star q star on your formula sheet. The tricky part is we're going to have two options for p star. Okay. And so here on your formula sheet, I should confirm, I guess. Phew. I did my math right. Z star over m squared times p star q star. That's on your formula sheet. So you don't need to do the math to get there, but I wanted to show you that it's just from the confidence interval, the margin of error. So first thing to note is that q star, whoops, q star is of course 1 minus p star. So everything just hinges on what the p is, and then the q just follows. Okay. We have two options for p star. Option number one is if we have a previous study that we can use, then you can use that p hat as your p star. Okay. So if we have a previous study with a p hat, so some sample proportion, then we can use p star is equal to that p hat. That's assuming that we have knowledge about the population. Okay. Now, the safest thing to do, but also it's going to give you a larger sample size that you need than probably what you need, but it's the more conservative approach, is to just assume a 50-50 split, successes, failures. That's going to maximize the N. And so here, the more conservative approach is to assume p star is 0.5, as this will give us our largest possible estimate for N. As this will give the largest possible estimate for N. So on the test and on the final exam, it's going to say either use the sample proportion or use the information from the previous sample to calculate the sample size, okay? Or it'll say something like, assume you have no knowledge about the population, and that's going to be what tells you what you use for your P star, right? If you have no knowledge about the population, you have to assume a 50-50 split. Okay? Now, another note that I want to make here is when you're solving for n is the sample size, right? And so after calculating n, we always round up to the nearest whole value. We always round up to the nearest whole value. Otherwise, your margin of error would just be slightly larger than what you wanted, right? So it's just a good rule. Otherwise, our margin of error will be slightly larger than desired. Oops, it doesn't say desired, does it? Which would be bad. You're fine having a smaller margin of error than what you set out to have. That's good. Because what does the margin of error say? It means it's just how precise your estimate is. So if you can tighten that up, then that's a good thing. But you don't want to have something wider than what you set out to do. Now, it's not really going to matter, right? But it will matter because your n, you can't collect 0.04 of a person, right? So as an example, if we found n is 110.04, we would need to sample n equal to 111 people, because I can't sample 0.04 of a person, right? And if I went down, even though proper rounding says 110, right? If I went down and I went backwards and I calculated my margin of error, it'd be slightly larger than what I wanted. So here, so we always round up for n. There are a couple of more kind of rounding guidelines coming our way. But this one, people tend to remember this one just because it makes sense. Okay, so that wasn't really a review or anything. It's just, here are some things. And there is an example here that we'll do. But any questions before we do? Oh, crickets. This description is kind of long, and it makes you think that we're supposed to do something else, but really what we want to know is how people understand sampling, or how well people understand sampling and proper sampling. And so two scientists want to know if a certain drug is effective against high blood pressure. The first scientist wants to give the drug to 1,000 people with high blood pressure and see how many of them experience lower blood pressure levels. Now, I think we know enough to say, well, okay, that's weird, because don't you need a control group? Yes, you do. The second scientist wants to give the drug to 500 people with high blood pressure and not give the drug to another 500 people with high blood pressure and see how many in both groups experience lower blood pressure levels. Which is the better way to test this drug, which is kind of lofty, but that's okay. And so it's always better to have a control group right? And so then you can compare and see, okay, blood pressures of those who get the drug, and then compare it to the blood pressures of those who don't. Yeah. So the GSS is a general social survey in the States, I think it is. I think it's called something like that. But it's just a big national survey that they do. So the GSS asks the same question, and below is the distribution of the responses from the 2010 survey. So 99 people out of 670 said that all 1,000 should get the drug, and that's the best way to test this thing. Whereas 571 out of 670 said 500 should get the drug and 500 don't. So what we're going to phrase that is 571 out of 670 had kind of good intuition about proper sampling. We can phrase each of these as a success, right? We can talk about the proportion of people who don't have good intuition about sampling in general, right? But we're going to talk about the proportion who have good intuition about sampling. So we want to estimate the proportion of all Americans who have good intuition about experimental design. So meaning they would answer the 500 and 500. So the parameter of interest is, of course, the proportion of all Americans, right? I want to know about P, the population proportion. My point estimate in this case is going to be my sample proportion. And for us, our sample proportion, P hat, is 571 out of 670. What is that? I have a feeling it's not anything nice. It's not. 0.8522388806 probably keeps going, but who cares? Just making a note here. X is 570. This is the observed successes. And N is 670. Okay. I can't tell what's on the next slide until I get there. Okay. For me, let me see here. I don't want to do this. Skip 2 slides. Because here it doesn't say calculate a confidence interval, so we can talk about this, but whenever I get you to do a confidence interval, it'll say construct a 90% confidence interval for the proportion of Americans who have good intuition about experimental design, something like that. But the key is that I'll tell you to make a confidence interval, which they haven't done here, and that's what is kind of ticking me off about that slide. Same thing here, we already kind of talked about this one. So here, this is what a question would look like, sort of. The GSS found that 571 out of 670, which we're going to use 85%. We know that's rounded, but that's okay. of Americans answered the question on experimental design correctly. Estimate using a 95% confidence interval the proportion of all Americans who have good intuition about experimental design. Okay. So first thing we're going to do, we're going to check the conditions, but we're going to kind of make it snappy here. It's a national survey. I'm going to have to assume that it was randomly selected. I don't think it said anything about it. In fact, here in this blurb, it doesn't, but we assume the sample was randomly selected. It's reasonable because it's a big survey, but it doesn't say explicitly, so then I have to say that we assume that. 670 Americans, 670 is less than 10% of all Americans. So that's good. And we're doing a confidence interval, so I have to have at least 10 observed successes and at least 10 observed failures. So n times p hat, but in this case I have x, which is 571, is greater than or equal to 10. At least 10 observed successes. And n times q hat, which is really n minus x. So 670 minus 571, we know from the table is 99, which is also more than 10. At least 10 expected successes. Therefore, conditions are satisfied. Something like that. I'm sure it has everything that we're about to do on the next couple of slides, but I want to do it together for practice. On your formula sheet, let's see if it's loaded yet, because that might be nice. Oh, maybe not. Eee. Finally. There it is. And there's the sample size calculation. Let me just grab it so you can see what it looks like on there, but it is the same, but it always feels different. I need my p hat. Now, we were told 85%, so I'm going to use p hat as 0.85. We can do the math and find that it's different, but because it's given here, I am going to say p hat is 0.85. Even though it's technically 0.85 to whatever. So I need my p hat, which I have from the question. I need my z star for a 95% confidence interval. 1.96, or you can use your table, but we were told to use a 95% confidence interval. P star or p hat again, 0.85, q hat 1 minus 0.85, and n is 670. So we have all the things that we need. So p hat 0.85 from the question Z star is 1.960 from the table, which let's see if it's loaded here. I guess I can copy it in. Why not? I'll put it here. Okay. And then I want a 95% confidence interval. And I need my Z star, which is going to be 1.96. And my N was 670. I can also do Q hat here is 1 minus 0.85, which is what, 0.15? Have all the things that I need. And so P hat plus minus Z star times P hat Q hat over N. P hat, I'm going to use the 0.85 plus minus 1.960 times 0.85 times 0.15 divided by 670. 0.85 times 0.1, wait, that's wrong. Don't forget the square root times 1.96. 0.85 plus minus 0.0270379511. Or 0.85 plus minus, I kind of lose any activity after the 7. And so then I'm just going to keep to 3 decimal places because 4, nothing would really change. And so I'm going to go to 0.027. I don't know if it's showing up there, but there's a cloud that keeps loading, which is kind of scary to me. So, see. To 3 decimal places. 0.85 minus 0.027. You always want to do the minus first, even though it goes plus minus. But because intervals have to go from smallest to largest, it's always better to just do the subtraction first and then do the addition. So 0.85 minus 0.027 is 0.823 up to 0.85 plus 0.027, 0.877. One thing to note here is this has a margin of error of 0.027. If you were unhappy with that and you wanted it to be 0.02, for example, right, have even more precise results, you would need to increase your sample size, right? And we'll be able to figure out what it is that we need. And so, but for now, we're just doing the confidence interval. Proportions are percentages, right? So 85% plus minus 2.7%, right? And so the margin of error can also be communicated as a percentage. This is only half the marks for a confidence interval. The other half is from the interpretation. We use the same standard blurb. We are 95% confident because I built a 95% confidence interval. The interval from 0.823 to 0.877 Then that keyword captures. Captures I like to throw in the word true, which is kind of hinting at the population. The true or the population proportion of all Americans, which again, all Americans is also hinting at the populations, but it's so important that we're talking about the population, right? It doesn't, I'm not upset if I see it many times. The proportion of all Americans, the true, maybe I'll cut the true, fine, because it is in there. The proportion of all Americans who have good intuition about experimental design. That last part, I'm just rewording the question as an answer, basically, right? So nothing crazy. Sounds fancy though, doesn't it? Or maybe not, I don't know. Good, nice. So I think the next couple of slides just walk you through that, but I think it's better to have done it together. This should actually have a p hat here. And then they land on the same interval, but then they skipped the interpretation, which I don't want to build any bad habits. We always interpret the interval. But now let's see an example where we're choosing the sample size. How many people should you sample in order to cut the margin of error of a 95% confidence interval down to 1%? Now, it's unclear to me. Let me just. How many people should you sample in order to cut the margin of error of a down to 1% from the previous 0.027 or 2.7%? Just to emphasize that it's linking back to that problem. Although we could just answer this blindly as well. Okay. Now from your formula sheet, when you're choosing the sample size calculation, oops, is down here. Copy. This is the only type of question where we do a sample size calculation. And so it's just kind of a one-time thing. It also kind of means that I have to put a one sample proportion question on the final exam so that I can test the sample size calculation. But that's nice, I think. Okay. So now we have Z star is still 1.960. That hasn't changed. All that's changing is I want my M to be 0.01 or 1%, right? Divide by 100. Your M has to be as a proportion, not a percentage. Okay. So N is going to be 1.960 divided by 0.01 times P star Q star. We said we had two options. for P star Q star. P star. Option 1, P star. I can let it be the previous P hat from before, which means that P star would be 0.85. Option 2 is I say, okay, forget that I ever had that information, right? And let's just say I know nothing about the population. Then I assume a 50-50 split, 0.5, 0.5. Okay. I'm gonna do option 1. Option 1, where P star is 0.85 here. And I'm gonna do option 2 down here or beside it. Says the same thing twice, but that's okay. If I have n is equal to 1.960 divided by 0.01 times 0.85 times 0.15. Oh, squared. Hee. Nice try, Emily. Squared both those, I forgot. .96 divided by 0.01, square that, times 0.85 times 0.15. I get 4898.04. Therefore, n would have to be 4899. Right, because we have to round up. This, we know, or we said, is the more conservative approach. So when I do the sample size calculation with P star equal to 0.5, I should get a larger value of n than if I have some idea about the population. And so if we do this, n is 1.960 divided by 0.01 squared times 0.5 times 0.5. 1.96 divided by 0.01 times, oops, square it. I keep wanting to forget that, times 0.5 times 0.5. I get an even 9,604. That's nice. No rounding necessary. It's pretty rare. Notice how we didn't have to have any information about the previous question in order to find this sample size, right? I was just saying, okay, you need to have a 95% confidence interval and you need the margin of error to be 1% or 0.01. And then you're able to calculate the sample size. Notice also that this is quite a bit larger, 9,604 versus 4,899. Often there are incentives to having people participate in your study, right? Have a $10 gift card, even a $10 gift card for participating in the study. That's going to add up. If you can get away with just sampling this number versus this number, right? Never mind the actual cost of having people doing the surveys and stuff. And so obviously this is way more expensive, but it is the upper level of what you would need to sample. Okay. And so here, this assumes no knowledge of the population / the previous question. But it is expensive to collect a larger sample size, but that's how you would kind of backtrack it. Whereas if you have some idea about what the population looks like, then you'll be able to kind of cut your sample size down, usually, right? But the closer it is to 50-50, the more you're going to need. Nice. So here, they did the work. They did it kind of different than how we did, but it's on our formula sheet. And so what if there isn't a previous study? Then we use 0.5. We don't know any better. 50-50 is a good guess. And it gives us the highest possible sample size. There's another typo here, p hat. We already discussed the conditions, right? I need at least 10 observed successes and failures if I have a confidence interval, whereas for a hypothesis test, I need at least 10 expected successes and failures. And the difference in calculating our standard error is going to be we need p hat instead of p naught. How about a hypothesis testing example? The GSS found that 571 out of 670, so 85% of Americans answered the question on experimental design correctly. That's the exact same blurb as before, right? So we can use the same blurb. And in the past, I was really kind of grilling my students, I guess, because I would always make them do a confidence interval and a hypothesis test for every single question. Now I am more relaxed. Do these data provide convincing evidence? Now this statement here is what tells you that you're going to be doing a hypothesis test. Usually I like to start with, is there evidence that blah, 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 blah. Okay, but any sort of mention of evidence means that you have to do a full hypothesis test. That more than 80% of Americans have a good, I don't know, intuition about experimental design. Doesn't matter. Now, if we have to do a hypothesis test, so for a hypothesis test, first let's check the conditions. Well, again, the first two we can copy from before because it's the same blurb, right? We assume the sample was randomly selected. Again, it doesn't say that it was, but we assume that it was. N of 670 is less than 10% of the population of Americans. Americans. That's the same as before. Same as the confidence interval. Nothing's changed there. What's changed is now I have to have at least 10 expected successes and at least 10 expected failures, which means I need to have some expectation, some hypothesized proportion. So I have my sample proportion, p hat is 0.85. When I'm doing a hypothesis test, I'm going to want to compare my sample proportion to some other proportion. And in this case, right, that proportion that I want to compare, my 85% is to 80%. Yeah. And so here, P naught is going to be 0.8. Specifically, we want to know if more than 80%, so significantly more than 80%, gave this answer on the survey. 85% is more than 80, but we want to know if it's significantly more, right? And so that's why we have to do a hypothesis test. But from here, the value that I want to compare my sample proportion to is my P naught. And so here, n times P naught is 670 times 0.80, which is 536, which is more than 10. At least 10 expected successes. And n times Q naught, which is 670 times 0.20, right? 1 minus 0.8, which is times 670. I don't know why I did that. 134. Which is also greater than or equal to 10. At least 10 expected failures. Therefore, the conditions are satisfied, which means that we can keep going with actual hypothesis tests. This is only our second example of a hypothesis test. So if it's feeling a little rough, that's okay. We'll get there. Like I was saying before, you have to do all the things in the steps, but you don't have to actually outline the steps like I do, but you do have to do it all and in this order. So why not? Step 1, state the hypotheses. Your null hypothesis from your formula sheet is that P is equal to P naught. But what we have is we have P naught equal to 0.8. So I'm going to replace this with 0.80. Right. I replace it with the value from the question that I want to compare my sample proportion to. Once I've done that, my alternative hypothesis just kind of falls out of this because it's also a statement about P and how P compares to 0.80. And from the question, I want to know if more than 0.8. So I don't care if it's less. In fact, I couldn't use 0.85 to prove that it's less than 0.8. And so I really only care about this one direction. And so here, P is greater since we want to know if more than 80%, blah, 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 blah. I also like to make a little note here that this is a one-sided test. I don't need that until step 3 when I'm finding the p-value, right? A one-sided p-value or a two-sided p-value. And so, so we don't need it for a long time, or what feels like a long time. And so that's why there's a disconnect, and it's kind of difficult for a lot of people. But if you make a note here, then you can kind of, okay, go back and get there. So really what I'm trying to show is that P is significantly greater than 0.8. But what I have to do is I have to assume that P is 0.8 until I have proof otherwise. So step 2. Calculate the test statistic or do the test is usually what I say. But I had to stop that because it was, then people didn't know what the test statistic was. And that's not good. But calculate the test statistic. The test statistic is the z-score that's on your formula sheet. Z is p hat minus p naught over the square root of p naught q naught over n. I have all these things, so I can just plug and chug now and say 0.85 is my p hat. How far is it from 0.8 if the standard error is 0.80 times 0.20 divided by 670? I'll do the numerator first, 0.05, and then 0.8 times 0.2 divided by 670, and I'm going to do the square root right away. Divided by 0.01545334819. $3.2355447776. That's a really large Z, right? Right away, I anticipate rejecting the null hypothesis because it's 3.2 standard errors above my hypothesized proportion, which, yeah, it can happen, but it's unlikely. It's more likely that it came from some other population. So what can we do? Step 3. Find the p-value. Let's see if it's still in my, no, in my paste. I was hoping the table was in my paste still. Copy. Come on. Okay. My calculated Z goes in the middle, and I like to throw a since in there. You don't have to. Since the absolute value of Z equal to, and you want to keep at least 3 decimal places. And if you're on the cusp of one of these, you'd want to keep more, obviously, but usually 3 is fine. 3.2, hey, 2355, something like that, is between Now 3.2355, is somewhere here. So it's between 3.091 and 3.291. This is where you need to remember if you have a one-sided p-value or a two-sided p-value. Right, and that was, like I said, it feels like so long ago that we set up the null and alternative hypotheses, but that's why I like to make a note, right? Because I want to know if p is greater than 0.8, which means I have a one-sided test, which means I need a one-sided p-value. So the one-sided p, so the one-sided p-value is going to be between these two numbers, but they decrease as you move further and further out into the tail. So then I switch the order because I like to just keep my inequalities the same. So 0.0005, 1, 2, 3, okay, and 0.001. So my p-value is very, very small. Once we have our p-value, then we can do our conclusion. Step 4 is the conclusion. Our conclusion has 3 parts, right? 3 subparts. First, you need to compare your p-value to your alpha level. It didn't give us an alpha level, so we have to assume 0.05, right? And so since our one-sided p-value is between 0.0005 and 0.001. That sounds excessive, and but I do want to see all those parts. You're really just saying what you found in the last part. So it's, you know, no extra work, it's just writing. So since our one-sided p-value is between 0.0005 and 0.001, it is less than our assumed alpha level of 0.05. Which means, I'll do a comma instead of a period, kind of a run-on sentence, which means we have enough evidence to reject H naught, which means we have enough evidence to reject H naught in favor of HA. If I'm rejecting it, I can say in favor of what? If I'm not rejecting it, you just end it there. What does that mean? Then we reword the question as an answer. Just gonna paste it in. I'll delete this, but therefore these data do provide convincing evidence that more than 80% of Americans have a good intuition about experimental design. Maybe I'll keep it there just to emphasize where it came from. Therefore, these data do provide convincing evidence that more than 80% of Americans I'm gonna cut the have good intuition. Oof. About experimental design. You don't want to forget that part. It's so tedious, but it's also really easy, right? If your p-value was not small enough, so not less than 0.05, your conclusion would be these data do not provide convincing evidence that more than 80% of Americans have good intuition about experimental design, right? Which is what we wanted to answer in the first place. Whew. So as long as you remember that your conclusion has those three distinct parts, right? Compare your p-value to your alpha level. Then what does that mean in terms of H naught? You either have enough evidence to reject H naught or you don't. Right? And then, of course, what does that mean in terms of the question? That's the end of that example, sort of, because we can also use confidence intervals to informally test a hypothesis. So we can use a confidence interval to informally test a hypothesis. Recall the 95% confidence interval for this question. And I'm just going to snag it. It's quite a ways up here. Oh yeah, we did the sample size. Man, it was a long time ago. Making me worried about how much time I have left. Let the good times roll. Okay. Copy. So much scrolling. Maybe I'll do this in a different color. If we're 95% confident that the interval from 82.3% to 87.7% captures the population proportion, right? That's all above 0.8, right? And so if your hypothesized proportion is outside of the interval, then that's enough kind of evidence to reject H naught informally. So notice that the null hypothesis P is equal to 0.80 is not in the interval. Which means I'm 95% confident that 0.8 is not the population proportion. It's not really what it is, but kind of. How I like to think of it is on this number line here. If I have 0.823 up to 0.877, I'm 95% confident that the true population proportion is somewhere in here. Right, so here we're 95% confident P is in here. So then if I'm hypothesizing that P is 0.80, well, I'm 95% confident that that's not the case. There's a chance that I'm wrong, blah, blah, blah. But if I'm 95% confident that somewhere in here is where my population proportion is, then that's evidence against P being 0.8, right? And so here, since P equal to 0.80 is not in the confidence interval, we have enough evidence to reject H naught. So it's an informal hypothesis test because we don't have the P values and things like that. But if I have a confidence interval, then I can get a good idea of what I'm about to do with my hypothesis test, right? Just by looking to see if my hypothesized value is in the interval or not. So versus if my null hypothesis is that P is, I don't know, 0.83 or something, what would that look like? Then I would still have my interval 0.823 up to 0.877. But now all of a sudden my 0.83 is a plausible value for the population proportion. So in this case, I would say since P equal to 0.83 is in the interval, we do not have enough evidence to reject H naught. So if it's in the interval, you do not have enough evidence to reject H naught, but if it's outside the interval, then you do have enough evidence to reject H naught. Kind of a fun way of merging the two. Of course, there is that relationship between a default 95% confidence interval and an alpha level of the remainder, the 5%, right, 0.05. And so they are related that way, but that's kind of beyond this course. You can get there, but it's okay if you don't. Okay. This is using what's called the Z table. We're not using the Z table this term. And so we could use software to find the actual p-value if you wanted to. But we had the range, and the range was really small, right? Between 0.0005 and 0.001, while 0.0006 is between those two values. Don't make me say them again. And so we reject H naught, and that's the exact same as we found before. Okay. Any questions before the next example? Okay. 11% of 1,001 Americans responding to a 2006 Gallup survey stated that they have objections to celebrating Halloween on religious grounds. 95, hey, how apropos, because it's Halloween next week? I used to have a better handle on Halloween, I guess. At 95% confidence level, or at a 95% confidence level, the margin of error for the survey is plus minus 3%. That plus minus is just a reminder that it's in your confidence interval, and it's that plus minus chunk, that buffer. A news piece on the study's findings states more than 10% of all Americans have objections on religious grounds to celebrating Halloween. At a 95% confidence level, is this news piece's statement justified? So, what are we really saying? My p hat is 0.11. My n is 1,001. The margin of error is 0.03. It's common to report the margin of error for proportions as a percentage, but for any math that we do, we have to use the proportion, of course. Okay. So what does this look like? Well, I have p hat plus minus m, technically. So if I have a p hat of 0.11, but my 95% confidence interval requires a buffer of 0.03, what I have is 0.11 minus 0.03, whoops, not 0.011, 0.11 minus 0.03 puts me at 0.08, and 0.11 plus 0.03 puts me at 0.14. So we could write this out and interpret this, and we could say, okay, we are 95% confident that the interval from 0.08 to 0.14 captures the true percentage of all Americans who have objections on religious grounds to celebrating Halloween. But more than 10%, I can't agree with that, right? Because if I have my interval here, 0.08 and 0.14, well, more than 10% would have to look like this. But that's not the case, right? 0.10 would be in here somewhere, right? So what they're saying is that it looks like this, but really 0.08 and 0.14 wrap around 10%. And so you can't conclude that it's more than 10%. So not more than 10%. Oops. So is the news piece's statement justified? No, it is not. Because it wraps around 10%. Nice. Speedy Gonzalez. What am I gonna do? This is just a recap of the conditions, but I feel like we've really harped on those. And then here we have 6.2. But I kind of feel like that's a nice place to stop. Is it too early? Other things you'd rather be doing, maybe. I always feel weird ending early. It's there. I'm sure you have other things to do. There's an assignment posted, for example. But if you have any questions, I'll stick around. But otherwise, enjoy your weekend, and I'll see you on Tuesday.